I'm really delighted to introduce our first speaker. I have seen her work over many years now, and this actually was my first chance to actually meet her, but we were really happy that Jana Sillmann accepted our invitation to come and give the opening talk this morning. So Jana Sillmann is going to be talking about assessing climate extremes across scales. Take it away.
Thank you. So, how do I do that? Okay, hope it comes up. Yes. Yeah, thank you very much for the invitation. I'm also delighted to be here and able to present my work. And before I get started, I want to thank all my colleagues that were involved in this work that I'm presenting here, and that contributed, which there's many colleagues, so I didn't put them all up here, but you will notice on the papers that I'm citing who I'm thanking here. This one. So let me get this under control. Yeah, so my talk will be about assessing climate extremes across scales, from global to regional climate modeling. And most of you, or if somebody knows my work, it was mainly about global extremes. And here I'm trying to bridge a bit the global work that I've done with the regional work that I'm doing right now. And the climate extremes is now one of the World Climate Research Programme's grand challenges. The challenges on understanding and predicting weather and climate extremes. It is challenging because we're talking about so many different scales, from temporary, spatial, and just starting with climate extremes or weather extremes where we feel the impact very locally. We want to understand why they happen, why they have an impact, but to do so, to predict them and project them, we need global models and we need regional models to get down to the scales where the extremes actually have their impacts. So when looking at climate extremes in model simulations, regional or global, we are challenged with several issues. First of all, it's in the definition of extremes, which are rare in space and time. And so it's really difficult to sample them or to have a good record to study or analyze them, instead of like looking at mean temperatures, for instance. And then we have, when we try to define extremes, it's very difficult to find one unique definition for extremes that happen across different regions, for instance. And then that comes also with the definition. And being rare, we have a lack of observational data. In some regions, that's Africa, South America, we don't have observational data to study extremes. And then even if we have observation data, we have a scale mismatch between a point observation and a model output, which is on a grid average. And so in the IPCC report, they tried to tackle these challenges by addressing extremes with indices. This is one way to define or find universally valid definitions, extreme events across regions. And I will talk a bit more about these indices in my presentation. And then we have also extreme value analysis, where we can calculate, for instance, return values such as a 100-year flood. So in my talk, I will go on to talk about climate extreme on a global scale. I will present results from the model evaluation and future projections that were presented in the IPCC report. I will discuss a bit sector-specific climate indices, and then I will go over to the regional modeling. So, climate extremes on a global scale. There is this WMO, Commission for Climatology task team, expert team on climate change detection and indices. And this task team, expert team, had a mandate to monitor climate extremes. And for that, to monitor, you need an observational record of the climate extremes. And that was the first challenge. And so what they tried to do, they tried to get daily data across the globe to calculate indices to monitor extreme events. And the indices were one way to get daily data or to get information about extremes in areas where there's not much daily data available, like where it's not openly accessible. So they do workshops in regions like Africa, Asia, to work with the people there that have the daily data, and then they calculate these climate change or climate extreme indices, and then they put it in a data set. So we have a more globally available data set of climate extremes. And that work also was helpful then in terms of looking in the climate models on extremes. So this expert team developed a set of 27 descriptive indices that are supposed to describe the distribution in terms of climate, all the climate characteristics. For instance, they have indices that are based on thresholds. For instance, frost days, they address the lower tail of the distribution, like all days below 0 degree centigrade, or they have, for instance, indices that address the upper tail, which is like summer days, days above 25 degrees. And then they have indices that address the precipitation distribution, so they characterize indices across a wide range of characteristics of extremes. And these indices were used in the recent IPCC reports, starting with the forest assessment report, where we saw already the changes in extremes captured by these indices. Then we had the special report on extreme events, where also these indices were used, here consecutive dry days. And then now we have the most recent IPCC report from 2013, where we used CMIP5 and CMIP3 models, and also used these indices to show future projections of changes in climate extremes. But what was special about this IPCC report, in comparison to the previous one, is that for the first time, we were also able to evaluate these extreme indices. And that is reflected here in this table, which is taken out of the last IPCC report, where we try to make it the use of these indices. Here's a range of these indices that were used across chapters in the IPCC report. And we try to be consistent in what indices we choose across the chapters. And then also here you can see, for instance, consecutive dry days. We used it in the observation chapter, we used it in the model evaluation chapter, and future projection chapter. So that gave a more consistent idea about observed extremes and evaluation of extremes in models towards projections. And it was possible because this great work from the people in Australia, led by Lisa Alexandra, and this website is from the CLIMDEX work, where they used these indices, the data that got collected by the expert team for climate change indices, and they gridded all these indices. And on this website, you can find it under data sets. You get the gridded products of these indices based on observations. And for some indices, the coverage is quite good globally. Other indices, for instance, precipitation indices, we have quite big gaps over South America, Africa, and other regions. But with these maps, we can really monitor, we can see how the extremes changed in the past decades. And these results were then in the IPCC report chapter 2 on observations. So what we did now, we used these data sets, the gridded products of these indices in climdex.org, and we consistently, with the definition and code that was used for these observed indices, we calculated the indices for different reanalysis sets and global climate models from the CMIP3 and CMIP5, which all went in an openly available, publicly available data archive where you can download the indices. So out of this database and all this data work, we were able to do model evaluation and future projection for the CMIP5 models. And this is one very complex figure from the IPCC report, where here we see again the range of indices, precipitation indicators, and extreme temperature indicators. Here we have a range of CMIP5 models, and each of these triangles represents one reanalysis. And what stands out of this graph, which was very common to use for other variables also in the chapter 9, but here for the extremes we see that this is very colorful. And there are basically three main messages. We can see that even for the reanalysis, looking at one particular variable, for instance, let's see, frost days, we have for this one reanalysis, it is very good, the results, and for others it's not so good, the consistency with the reanalysis. The models with the reanalysis. So we have differences between the reanalysis that can be as large as the model spread, and that again shows we also need to evaluate our reanalysis, and for that we need a better better coverage of observations, which often for these indices we don't have a global coverage. So we cannot do this figure in a global manner. And then model and reanalysis performance depends on the region and index under consideration, because you can see some indices have a very good performance and other indices, precipitation indices in particular, are very challenging for models to capture. Here's one example from the model evaluation which illustrates one issue, for instance, we picked out with the reanalysis. We have here the coldest daily minimum, so one index, and we have here the green is the CMIP3 model ensemble and the spread, the mean and the spread. The gray is the CMIP5 model ensemble spread, and the black is the median. We have one particular model, the NORISM, just as an example, that for this particular index, it's very well within the model spread. And then we have the reanalysis, where you see they're very far, the NCEP-based reanalysis are far off from the ERA interim or ERA reanalysis. Another index capturing the hottest temperatures, for instance, we have a different picture. We see that this one particular model is way out of the model spread. Some of the reanalyses are closer together, but one particular reanalysis, the NCEP1, has a big problem with this particular maximum temperature indicator, especially over the tropics. It has this artificial jump, which you have to be aware of when using reanalysis for evaluating models. Okay, so now that we have confidence in or we gain some confidence in how well the models are able to represent the climate extremes, we look into the future, and these kind of maps and graphs we have seen in the previous IPCC reports that minimum temperatures increase much more in the northern latitudes than in other parts of the world, and the maximum temperatures increase more on continental scale. And here also these maps for precipitation, for instance, that we have a almost 3 times increase in extreme precipitation globally than for mean precipitation, particularly in the northern latitudes. And then the consecutive dry days, an indicator for drought conditions. We see some key areas like the Mediterranean, Australia, Southern America. And but what we cannot with these indices and these global maps, we cannot really address any needs of users or the sectors, and they're really abstract in terms of providing information that is relevant to users. This is very abstract. And so we need better indices to support adaptation, decision-making, climate services, more tailored products. For that, we have these sector-specific climate indices. There was a new team created by the WMO Commission for Climatology, which is the expert team for sector-specific climate indices. And they now define indices that can be applied across a wide number of sectors like health, water, agriculture, and also a wide number of regions. And so they developed this ClimPact software, which is based on the software that we used for calculating these 27 ETCDI indices, but now is much more expanded to suit the needs of regional users. So what they do, they use this same concept of workshops going into the different regions in Asia and Africa and work with people there that have daily data and also that have needs for information of climate extremes, like for instance farmers or the health sectors. And then they work out together what are important thresholds, what are important variables to look for, and then they put it in their ClimPact software, and then they can calculate a much wider range of sector-specific indices with this software. Yeah. And so going now to the regional scale. That's really getting to the scales of impacts, because the impacts of the extremes we feel at the local to regional scale. And this is across, again, different time scales. So when going into this regional direction, we are even confronted with even more challenges. Because we have global climate models which we need to simulate the global, for instance, global circulation, the modes of variability that can drive extreme events. And we have reanalysis at scales similarly or in between the global models and regional climate models, resolution spatially and temporally. Then we have the regional climate models. And then, if we want to do a similar exercise as with the global models, we need the observations to evaluate what the regional climate models do or the reanalysis. But do we really have the necessary observation to do that at the scales we need? Like, for instance, hourly, sub-daily observations of precipitation. And as mentioned yesterday in the panel discussion, we don't have, for instance, even for Europe, a consistent data set, gridded data set for small-scale observations. So that's a challenge. But I give you some examples here how we used observations for assessing climate extremes in different regional climate model ensembles. Here an example for extreme heat waves where we used the EOPS, observational gridded data set, which is good for temperature extremes to look at them. And here we picked out in this paper on the top 10 European heat waves. We looked at how observed extreme events like the Russian heat waves are captured by a new index, the heat wave magnitude index. And then we looked whether we find similar extreme events as in the observations, also in regional climate models. We used the EURO-CORDEX ensemble for the historical period and different combination of regional and global climate models. And then we can see that some of the models, and a few, not even all, can capture an event that as big as the 2003 heat wave, but none of them was able to capture the most extreme magnitude of the Russian heat wave. And then we looked into the future, how these kind of extreme heat waves will change in the future. Here, RCP 8.5 for the next few decades. And we see that each of these models has at least one extreme heat wave, such as the Russian heat wave, simulated for the next few decades. But this is an example. The extreme heat waves that were represented are in different locations at different times in these 30 years. So it's how do we deal with this, this spread and this information. And then we also looked at heat waves in CORDEX Africa. Here we look at the historical period of 1980 to 2015. This gray is the spread of the CORDEX ensemble regional models. The black is the ERA interim reanalysis. And we can see for different heat wave magnitudes, the larger the number, the larger the intensity of the heat wave. We can see that in the last recent years, in the reanalysis, we had 3 major extreme heat waves in Africa, all coinciding with an El Niño event and a severe drought. And we have the models which are able to capture extreme events of that magnitude, not in the same exact year, but the models can capture such extreme heat waves. And then we also looked into the future, how will these develop in the next few decades. The other extreme is, for instance, we looked at cold spells, and as I said here, these extreme events coincided with El Niño events. So the large-scale patterns matter. And are we able to capture this in the region with the regional models to really have the right climate variability signal in the regional climate model simulations of the extremes, because they can amplify the occurrence of extreme events. And that's what we investigated in this paper on cold spells and atmospheric blocking, because atmospheric blocking, which is a high pressure system which blocks the prevailing westerly flow, and brings in very cold temperatures. In Europe is the case, and also in North America, where we looked here at regional climate models in North America. And what we see here, that's an observational data set and 2 reanalysis, looking at differences in return values of minimum temperatures per extreme blocking or blocking occurrence, like high blocking occurrence versus low blocking occurrence. And we can see in the observations and in the reanalysis, there are areas where when we have a block, the temperature is much colder, so we have a higher probability of cold spells. And can we capture that in different RCMs was the point of this paper. And you see that there's some discrepancies between the regional models and also with the reanalysis and observations. Now going to extreme precipitation. Here resolution, spatial resolution, temporal resolution becomes quite crucial. If you see here, it's the global model from Norway, the tip of Norway, southern Norway. Here we see the topography of the actual topography in the regional climate model from Norway. And this is for a 3 by 3 kilometer resolution, which comes quite close to the complex topography we have in Norway. So when trying to simulate extreme precipitation in Norway, where we have fjords and high mountains, it becomes crucial that we go high resolution to really capture extreme precipitation at a realistic manner. And so we did this with the GCM, looking at summer precipitation at the regional climate model at 3 by 3 kilometers, and we can get quite realistic with the precipitation distribution and magnitude when we go to such high resolution scales. This is work by my colleague Øyvind Hotnebrock. And but when we go and when we look into extreme events, and as I said, we used a lot the indices so far in the global climate modeling environment, which also can be useful for a regional climate model to enable comparison between models and also reanalysis and hopefully observations. But there are other ways to calculate extreme events, for instance, percentile indices, like for instance the higher percentile, 99th percentile of precipitation, and extreme value statistics where we fit the general extreme value distribution to the maximum precipitation event, for instance. And these approaches are complementary and should be used according to a given context or scientific question. But we also need to be careful when looking at extremes and using different definitions of extremes, because the definition can matter, as is illustrated in this paper by Christoph Scheer, where we kind of tried to show that it makes a difference if you calculate precipitation percentiles based on all-day percentiles using the whole distribution of precipitation, or on wet day percentiles using only precipitation above a threshold like 1 millimeter, which is often used in the literature to avoid like the drizzling effect in models or these kind of things. So they use a 1 millimeter threshold and then they calculate the percentiles from the distribution. And then this is just the theoretically example where we can see here, for instance, this is the current climate, this is the future climate. And here we illustrate a decrease in the distribution of, or in the high frequency, in the high percentiles of precipitation. We have a current climate, the 80th percentile, and then in the future climate, with the shift of the distribution, we see a decrease in this percentile. But when we use the same distribution, but looking in only wet day percentiles, we see an increase in these percentiles. And we did that also with actual climate model simulations, looking at, for instance, the ensembles, regional climate model simulations. Yeah, okay. And here, future scenario versus present climate. And here we see the picture, how it looks for all day percentile indices. So we see here a decrease and an increase in percentile. But when we only base it on wet days, we see not this decrease in the precipitation. But that gives some confidence in the other indices we used so far. It's the 20-year return value. It shows similar patterns, and also the RX1 day, one of these ETCDI indices, shows a similar pattern as the all days index. And if we go even to high resolution RCMs, here it's a 2 kilometer resolution, and hourly precipitation, this discrepancy between the changes in percentile indices versus all days versus wet days, here we see over the Alps, we see a strong decrease in the percentile index, and for the wet days we see a strong increase, and this is even more obvious for the wet hourly precipitation. So when we go to higher resolution, we have to be careful what definitions we are using to look at changes in extremes. And so I want to finish with some outlook, or what I'm trying to express here is basically that we need, for going from global to regional and to really to the local scale, we need joint community efforts. And this means working with these expert teams from the WMO, working with the WCRP Grand Challenges on Climate Extremes, and working together with the WCRP CORDEX community on these challenges that I addressed. And one good example of such a joint community effort was a recent workshop, CLIP-CES-ENES, a joint workshop on common CVs for climate indices. This workshop was meant to bring some order in the metadata and the indice names, definitions, metadata, and also units of all these vast range of indices that are existing. And then because we want to, at some point, we want to feed these indices in the Air system grid, we want to make them available. So it's important that we work together and have a consistent way of calculating these indices and a consistent metadata available. And so just an outlook where I hope we can cross the scales when we look at extremes, because we need the global to also understand changes in the regional or local scale extreme events, and we need to work with the impact communities together with our global and regional climate modeling efforts to really come towards understanding and predicting climate extremes on multiple scales. Yeah, thank you very much.
Thank you, Jana, for that great overview. We have time for a couple of questions. I am going to cut questions off after a certain point because we need to stay on schedule, but Rasmus.
Thank you for a nice presentation, Jana. I have one question, which is not to you, but actually to the whole community, and as two missing perspectives on extremes that were ignored by the IPCC, but also the WRCP. And one of these things is to count the number of events as a Poisson process, because you can model that using the Poisson family in a regression. The other thing is record-breaking events, which is emerging as well, and that's also a very powerful way of actually detecting whether you get more extremes. And I haven't actually seen any of these actually referred to in the latest IPCC report, and I wonder why. Is that because people don't see this as useful, or because they don't understand or haven't actually heard of these aspects of extremes? These are more sort of statistics sort of based, but I just wanted to hear if you have any thoughts about that.
Yeah, so thank you. About these record-breaking events, I mean, there was a part of it in the IPCC because there is a citation of Camus and Ramsdorff's paper, which also used record-breaking events. But it is the work I showed was a great effort from different people across the world to come up with these consistent observation, reanalysis, global, and we had to use something on the definition. And of course, as we go along, we can use more and more, as I said, definitions vary across climate extreme. We can use more ideas and more concepts to include that, but it's difficult to come up with such a consistent concept to illustrate basically past events, future events, and evaluation to future projections. So it was a big community effort, but of course we have not yet included all aspects, and that's why the community needs to work together, and so we can cover all aspects maybe in the next IPCC report.
Okay, thank you, Jana. We do have to move on. Certainly, you can talk during coffee breaks further about this. Our next speaker, now we're going to, after that nice overview, we're going to be moving on to specific regions. And our next speaker, Emilia Diaconescu, is going to be talking about precipitation extremes in northern Canada.
Hi, my presentation will be on the daily precipitation and temperature extreme over northern Canada, estimated from Arctic and North-America CORDEX simulation and reanalysis. After a short description of datasets and climate indices that I'm using in the presentation and the study, I will present some results obtained in evaluating the climate indices from reanalysis and RCM historical simulations over a reference period of 25 years. We are evaluating the climate mean of indices as well as the spatial temporal distributions of anomalies of indices. We are using, in fact, a large variety of climate indices defined and by the expert team of climate change detection and indices. In fact, we are using indices that are based on the daily minimum temperature, on daily maximum temperature, on mean daily temperature, as well as on daily precipitation. All these indices are computed on as annual indices, and some of them are modified to be adjusted for the region of study, as for example, we define Arctic summer days with the thresholds for temperature greater than 50 degrees Celsius. We are using simulations from Arctic CORDEX, most of them from Arctic CORDEX experience, realized our 4 regional climate model with HIRHAM 5 model, with the CAN-RCM 4 model, with RCA 4 model, and with the CRCM 5 model. For the RCA 4 model, we are using both configuration with and without spectral nudging. Concerning the simulation with the CAN-RCM 4 model, we are using simulation with 2 resolution at 0.22 and 0.44 resolution. All the other resolution of simulation have a resolution of 0.44. And all these simulations are run over the historical period, are driven by different GCMs. But this ensemble of Arctic CORDEX simulation, we have added 2 simulations that are realized with the CRCM5 model and that are run over the North America domain. The region of analysis is the Arctic, Canadian Arctic, and it's represented in this figure in deep green color. And the figure also shows the domain of integration for the Arctic CORDEX simulation in blue, and also the domain of integration for the CRCM5 North America simulation. This last domain is a little bit larger than the standard North America CORDEX domain. It incorporates entirely Canada, and for that we can add it to the ensemble of CORDEX Arctic simulation for the analysis on this particular region. We also evaluate climate indices from 5 reanalyses from ERA interim, from GRA55 for CFSR, and also for GMFD dataset. This later dataset is a reanalysis product that is adjusted, is corrected with observations. We added at this analysis a dataset of gridded observations that is named NRCAN, and is a result of annuspline interpolation of observation over Canada, and offer results at a spatial grid of 10 kilometers. However, we did not use this gridded observation for evaluations because northern Canada is a region with sparse observations. And in these 2 figures, I present the location of station for temperature and precipitation from 2 sources, from the Environment and Climate Change Canada, and in general, gridded product based on such sparse network of observation have quite large errors, and for this particular region, we made the evaluation at station level by selecting the reanalysis and the simulation grid point closest to observations. We use stations that have at least 50 valid years in the reference period, and 1 valid year is defined as a year that has at least 20% of missing data. Finally, we will have 47 stations for temperature and 79 stations for precipitation. They are presented in the 2 figures in red, the red points. I will present first some results obtained for the evaluation of climate mean of indices over the reference period. And the figure here presents as an example only the annual precipitation over Canadian Arctic from observations. This region I show to show this figure because precipitation over this region is in general of small intensity. We use as metric the reduction of variance or the mean square error normalized by the variance of observation. This metric is a spatial metric. Therefore, the sum in the metric is done over all points situated in the domain. Positive value for this metric will show where the dataset has skill, and negative value means that the mean square error for this dataset is greater than the variance in spatial variance in observations. Results are summarized in this heat map that show the reduction of variance for all datasets and all indices. Each line corresponds to the primary figure. Each line show a different dataset, and each column corresponds to a different index. Next to the primary figure, we present also the average skill for simulating all indices based on temperature and all indices based on precipitation. It's all T and all PR. In general, figures show that reanalysis and models has good skill in simulating indices based on mean precipitation and on maximum temperature. However, they have difficulty in simulating, in general, the annual cold extreme and the number of wet days and the total precipitation from extremely wet days. Also, if we compare the Kenner CM4 simulation to the resolution, we can see that we can see that in general, the higher resolution, the 0.022, has larger, better scores than the 0.44 simulation. If we compare now the RCM4 simulation with and without spectral nudging, in general, it is the simulation without spectral nudging that has a better score compared to the simulation that is using spectral nudging. We also synthesized results regarding the ensemble mean of reanalysis, of the 5 set of reanalysis, and the ensemble mean of all simulation, and they are presented in the top of the figure, the scale score for each indices. And I present also some detail for 3 indices. I choose to show you the cold extremes, cold annual extreme, the RX 5-day index, and the precipitation, total precipitation due to extremely wet days. This figure presents the violin plots that show the kernel density estimation of the underlying spatial distribution. The figure shows the ensemble mean of reanalysis in green and the ensemble mean of simulation in red, each point in the domain. And we see that for the cold extreme, in general, reanalysis have a positive bias, while the simulation have a smaller bias, but negative bias. Both reanalysis and simulation have a good estimation for the RX 5-day index. However, they both underestimate the total precipitation that is coming from very extremely wet days. If we regard the top figure, we can see that in general, the reanalysis for most part of the index presents greater skills than the ensemble mean of simulation. However, if we analyze each simulation's comparative to the reanalysis, we can see that there are some simulations that has better skills than the mean of reanalysis. This can be better view in this figure, which show the mean square error for each data set normalized by the average skill of the 5 set of reanalysis. Positive values are represented in green and show where the simulations have better skill than the average skill of reanalysis. We can see that there are some regional climate models that have skills for the cold extreme and for the most part of precipitation indices better than the average skill of reanalysis. We completed the analysis with the spatial temporal distribution of anomalies for each index and each data set. For comparing the spatial distribution with that of observation, we choose 2 metrics, the Kuiper distance that measures the distance between 2 corresponding empirical cumulative distribution, presented in an example in first figure, and also the Perskin skill score that compares the overlap between the probability density function for the 2 samples. The second figure presents an example. We, in fact, using 1 minus p to compare the 2 metrics in the same way. And the example here that I choose to show is for showing you that a value of around 0.1, it's representing simulation that have very close distribution. All results are summarized in the performance diagram presented here. Each box shows in the top triangle the Kuiper distance, noted with D, and in the bottom triangle, we are showing 1 minus p Perkin skill score. we observe that for most part of the indices, reanalysis and the models have, in general, good skill in representing the spatial temporal distribution of anomalies. The value for the two metrics are below 0.2. There are some indices where it's more difficult, so for example, the heating degree days and also the total precipitation due to extremely wet days. However, if the anomaly for each simulation are pulled together to construct only one simulation PDF, as represented in the top of the figure, we can observe that even for this index, we have better score than for individual simulations. And this example clearly shows that the distribution, even for the extremely total precipitation from extreme wet days, for simulation and reanalysis are quite close to observation. Some differences came from the variance, as can be seen in the first figure here. In conclusion, this study has the purpose to evaluate climate indices from 12 regional climate models over Canadian Arctic and from reanalysis. We find that the reanalysis model have, in general, good skill in simulating the mean temperature indices, the warming stream, and the RX 1-day and RX 5-day indices. However, some difficulties are found when evaluating the cold extreme and the total precipitation from very wet days. Some simulations have better performance in simulating precipitation indices than the mean performance of reanalysis. However, reanalysis overperform the model for temperature indices, and we find good skills for the spatial temporal distribution of anomalies. In the end, I would like to thank to all these wonderful people for providing the data set that we are using in this study. Thank you.
Thank you. Thank you, Emilia. We have time for one, maybe two questions, if there are any. Well, I had one thing that I wonder about with these comparisons at times, especially with precipitation. I believe the observations were all station observations.
Yes.
So what are your thoughts about station observations compared to gridded model output?
The best thing is to use the same scales, but in this particular region, we don't even have the chance. All we can do is to use the station because they are quite sparse, and even in the north, you have only some station. The idea is that selecting the point and using more distribution than other things, we sample the overall distribution like that, and comparing the sample of models with the sample of observation, we can fit it together. But a better thing is to do like we do when we have the grading, to have the same scale to compare it. But here, the great challenge is we don't have it. And I think the solution is to use this kind of distribution and to sample the real distribution.
Good. Thank you.
Thank you.
Okay, moving on. Now we're going to move to another region. Philippe Drobinski is going to be talking about precipitation extremes related to temperature in the Mediterranean region.
Yeah, there's a pointer.
There's a pointer. You can also advance the slides.
Yeah. Okay, good morning, everyone. So, my talk will focus on the Mediterranean region, and I will address the question of precipitation extreme scaling. This work is the result of many contributions from many co-authors involved in the CORDEX and HIMEX programs, and this is also part of a cross-cutting activity conducted in the frame of GUEX. So when dealing with the evolution of precipitation extremes in a changing climate, we often try to see how the precipitation extremes yes, this one. Precipitation extremes evolves with scale with temperature, and we generally plot this type of diagram. So here, plotting the precipitation extremes as a function generally of daily surface temperature. And this is just an example of what we've done previously with special focus in southern France. And if we consider Clausius-Clapeyron equations, so we should have precipitation extreme scaling with temperature, meaning that the amount of water that falls from precipitation should increase with temperature. And here we found, so from a large number of stations, and one single CORDEX simulation, that we have a hook shape present in the scaling. The first part, which is associated to winter frontal precipitation and spring convection, follows the Clausius-Clapeyron equation. But at larger temperature, especially during summer, we have aridity, lower precipitation efficiency, and a drop in the scaling. So our questions were, first, we wanted to address, to really question the relationship between maximum water vapor content and precipitation extreme. Wanted to know a little bit more, why do precipitation extremes differ from CC scaling, from Clausius-Clapeyron scaling? Is generally this approach is used as let's say, to have a kind of predictive scaling for future climate? So is it standing here? And is the scaling spatially variable over the Mediterranean region? So what we did is we used a number of observations, in situ observation from the HIMEX program, providing temperature and precipitation from 10-minute time sampling to daily, to 12 hours, which were transforming daily precipitation in 6 locations around the Mediterranean. Also, we used, and this will probably be also a reply to Bill's comment, we also used grid products here with the EOPS, which provide temperature and daily temperature and precipitation over the whole Mediterranean. And we use 14 RCMs from the CORDEX experiment. Here, RCMs are combined also atmosphere, ocean coupled regional climate models, and also varying horizontal resolutions. So we have here temperatures, precipitation at 3 hourly time sampling for the whole Mediterranean. So these two can give really geographical patterns. I will not show everything. Of course, this is a paper that you can find in Climate Dynamics. So the method is we selected rainy events, and we sorted them in increasing order of temperature, daily average temperature. Here I will only show daily, but we also investigated sub-daily, 3 hourly, and we binned them in a set of samples, and we arranged them to perform the plot that I showed just before. So first, just have a look at the observations. So of course, it's in present climate. So these are only observations. So from station, you see here, especially this one in Spain is very, very nice data set. So going from 10 minutes to daily. And here we compare with EOPS at various stations. And you can see that, of course, when you decrease, when you decrease the time, the accumulation time, of precipitation, you increase the slope of the precipitation scaling. But below 1 hour, there is no more sensitivity on the scaling itself. Well, the precipitation intensity still increases, but the scaling remains quite robust, and we see that this hook shape is still persistent even at very high resolution time sampling. Also, we can define a temperature break, which makes the difference between the CC scaling and the let's say the subscaling range, and we can try to plot that as a function of the, let's say, the longitude following these stations. What you see here, so we go from 20 degrees, here it's still 20, here a little less, here this one is 10, and you arrive in Israel, and you see that in Israel you have only a negative slope, meaning there is no longer temperature break. So how the model, so first results from here is the hook shape is robust to whatever the time sampling, which is different from previous studies for this one in Japan. And the temperature break decreases with, when going eastwards, so with increasing aridity. So how do the model perform? So here I just plot daily precipitation. So you have a number of models that are shown here, only a subset, here only the 50 kilometers atmosphere standalone simulations. And so here the daily in situ data, and here the EOPS. And what you see is basically the spread, the intermodal spread is large in terms of precipitation intensity, but the scaling is robust. So if you scale these plots as a function of the accumulated heavy precipitation, all the curves should collapse in one single curve, which more or less will follow this one. So this is first result, and the second is we see that generally all the models perform quite well. Here I don't show any, let's say, quantitative skill score, but all the models perform quite well in reproducing the shape here of the scaling, with here this negative slope over the in Israel. So the intermodal spread can be large. But the simulated scaling is quite well reproduces quite well the observations. So now if we go to future, and first, before going to future, we a very brief here a figure that compares the era interim, so the downscaling of era interim and the downscaling of the historical CMIP 5 runs, so for the same period, and you see that basically, I won't go into detail, but basically the two periods mesh well. We have similar spread, but the intensity is similar between era interim and CMIP 5 historical runs, and there is a good agreement between the two data sets. And now if we go to future, so these are, sorry, here, so I just extracted only three locations, 3 stations. So if we go to future, we first see that there is a shift in the scaling at all stations by about 4 or 5 degrees Celsius, and in some regions, but I would not say it's significant everywhere, we also have, let's say, a steeper slope in the historical runs than in the future, meaning that here the precipitation increase. So the temperature break increases by about 4 to 5 degrees centigrade, which is the average regional warming here. So no surprise, the temperature range with CC scaling, of course, increases in future climate, and the hook can be, in some regions, less steep, which is equivalent to an increased precipitation extreme intensity. However, of course, a simple constant temperature shift does not explain the evolution of the scaling. So here what we did is to analyze the temperature change as a function of temperature. And what is interesting here is that you have a very, very large intermodal spread. So this temperature is not robust between models, so meaning that for some models, I would say here, for example, compare this black one and orange one. So they match quite well at low temperature, so meaning in winter. But when dealing with summer, you see that the temperature change varies considerably between models. So there is a nonlinear scaling between temperature and temperature change, and a nonlinear distortion of the temperature scale is not enough to explain change in precipitation intensity, in change of precipitation intensity scaling. So what we did finally, is using this, temperature change relationship with temperature, we corrected the historical runs, so assuming this nonlinear temperature change and assuming a CC scaling. So we applied that. So here what you can read is the dashed line represents the historical runs, the solid thin line, the future climate projections, and the thick line is the corresponding corrected historical run. So what would be expected in the future if Clausius-Clapeyron assumption was met. So here, well, you can believe me, I will just show this orange one, which is quite clear. You can see from far here. So you see that this is the historical runs. Here you have the future runs, and when corrected, assuming Clausius-Clapeyron, so these curve collapse into one single curve. So the correction for Clausius-Clapeyron is quite applies quite well. So. The corrected historical runs agree with scaling precipitation extremes in future climate projections. And applying CC scaling assumes some conservation, and especially conservation of relative humidity. And this was quite surprising, because we know, and all the global climate models and also all the regional climate simulations show warming and strong warming and drying in the future, and it's already observed. So we thought that there would be a trend of relative humidity at all Mediterranean sites, and so it was quite unexpected to have this absence of trend. And so what we did here, it's just a result for one single model. Here it's the humidity change with respect to Clausius-Clapeyron. So it's one when indeed the water, so the humidity, well, when relative humidity is conserved, is constant in a changing climate. And here you see that you have regions, very arid regions, where the relative humidity will decrease in the future. And this, at least these two regions are very robust in time, and this one is more is less robust between models. But these two, one and here in this region, this is robust. And what you see is that basically all the coastal regions are under the influence of the Mediterranean Sea, which provides enough moisture to maintain the relative humidity constant with climate change. And here we are under the westerly winds, which bring water from the moisture from the Atlantic Ocean. And here let's say the absence of strong mountain range allow like very large and breeze that can really advect moisture over Libya and Egypt. So here, this is just one figure that shows that, of course, over the ocean, CC scaling is, of course, is met, and so that's one so this is our let's say conclusion here. So relative humidity decreases in arid region. So continental Europe does not seem here. We're this is ongoing work, but continental Europe is probably not very very robust, but North African, Iberian and Arabic Peninsula is robust. Relative humidity remains constant in the regions affected by marine source of humidity from the European seas, and the Mediterranean Sea is a strong source of moisture which compensates expected relative humidity decreases. So this is my conclusion. So what we have in the Mediterranean is hook shape. Here it's just in Spain. So the historical runs reproduce quite well what was observed locally from stations here. And so it is a non-predictive scaling for what will happen in the future. But when we correct that, assuming CC scaling law, CC law, then we're able to correct for the signals. So the scaling of precipitation extremes in the Mediterranean displays a robust hook shape. In a drying and warming region, the Mediterranean relative humidity remains constant in changing climate, and so there is an increase of precipitation extremes, which apparently follows the CC scaling. And the Mediterranean Sea appears to be the origin of increase of precipitation extremes intensity. So with this pessimistic conclusion, I thank you for your attention.
Thank you. Thank you. We have time for one question. I'll go there since you already asked one before.
Yeah, thanks, Philippe, for this presentation. I think, to my understanding, the kind of analysis you show depends very strongly upon whether you use a precipitation threshold or not in the definition of your extremes. And you didn't state how actually you specifically do that, whether you use a precipitation threshold?
Yeah, I removed the 1 million, maybe 0.1, I don't remember.
Yeah,
yeah, there is a threshold to
well, all these extremes, they depend very strongly on whether you do that or not, and in particular changes in extremes. This is a point that Jana actually made in her presentation.
Sorry. But we did some sensitivity analysis on many things, threshold, number of samples, time, duration. We also, in a former paper, we analyzed also the effect of time sampling at grid resolution. So, well, I couldn't show everything, but yeah, but sure. I fully agree.
Sure. Thank you.
Yeah, good. Thank you. Okay, we do need to move on. Nice presentation, Philippe.
Thank you.
The last talk before the coffee break is Claas Teichmann, who is going to be Europe focused as well, but different topic.
Thank you. Let's see. Great. Okay, yeah, thanks for staying and not going to the coffee break already. So I want to talk very briefly about our assessment of extremes in the RCP 2.6 emission scenario and about the newly applied indices here we want to suggest and to have your opinion about this. So why do we want to look at RCP 2.6? In last fall, there was this historic Paris Agreement on climate change where 195 nations set path to keep temperature rise well below 2 degrees Celsius. So it's a very, very good goal, I would say. But if we achieve this goal, how can we assess what is happening then? So which extremes do we have to face even under low climate change conditions? This is the main question of the talk. So there was this Impact to Sea project where people were looking at what is happening from the impact side under 2 degree, under exactly 2 degree warming and under 1.5. And as you see here, for the different global mean temperatures, for the different scenarios, RCP 2.6, 4.5 and 8.5, not many simulations stay below 2 degree, actually below this goal. So we have to focus on the RCP 2.6 scenario here to assess what is happening if we achieve to meet this goal. And this is also what we can take for our discussion on Friday, that we need some of these simulations to assess this. Globally, there exist a bunch, but we will see that on the regional scale, there are not so many. So for 1.5 degree global warming, it will be exceeded around or before 2040. Only for the 2.6 scenarios, there it stays below. In all scenarios, except RCP 2.6, indicate that 2 degree will be exceeded around or earlier 2060. So this is just for background information you have to keep in mind here. So for the study we present here, we take the EURO-CORDEX simulations at the high resolution, because looking at extremes, it makes more sense going to 12-kilometer resolution. And we concentrate here on the historical runs and the scenario runs. And what we use here are 3 RCP 2.6 simulations. There's one more from Aladdin, which could not be included here, but will be included in the future. So there are 4 or 5 simulations ready, but for RCP 4.5 and 8.5, there are much more. So the RCP 2.6 ensemble is still too small for a robust assessment. So this, what I show here, just gives a first indication. So don't take it for granted. Okay, we start here with the heat days. For the 3 simulations that are included in the study, we have the heat days in the middle of the century, So policy relevance, for policy relevance reason, we chose the middle of the century, the change versus the control period, 1971 to 2000. So the order of the plot is always the same. RCA4, driven by ECRs, is on the left-hand side. In the middle is REMO with MPI-ESM, realization 1, and here's the MPI-ESM realization 2, the driving model on the global scale. And depicted here is the change in heat days, and we see that there's an indication for an increase of heat days in southern and central Europe mainly. And there the models, or the 3 simulations, I have to mention 3 again, agree relatively well that here we have always in the south the strongest increase of 8 to 10 and more heat days, while they are moderately increasing in the center of Europe. This has also to do with the definition here, number of days where the daily maximum temperature is exceeding 30 degrees. And it's also partly related, could be partly related to the driving model, where MPI-ESM is slightly warmer in this region like the ECRs. Okay, but this is quite interesting, but nothing special. More interesting is to look at the heavy precipitation events, which are defined in this presentation as the 95th percentile of daily precipitation amounts. And we are referring to for this indices also to the expert team of climate change, indices, what Jana was mentioning before. And here we see a bit of a more heterogeneous pattern, where we see certain regions like Spain here, where we have one region where the heavy precipitation events are decreasing, and on the other hand they are increasing here. And for the other simulations it's a bit vice versa, where you have a decrease at the coast and a more increase here, which is a bit similar here. But even the same regional model with the different global realizations show a heterogeneous pattern when looking at the increase. So our question was now, how can we assess the increase over a certain region without taking into account the exact location of the precipitation? This becomes even more clear if we zoom in. This case here is Scandinavia for obvious reasons. We see that also here it's the same thing as I showed before on the European scale. We have an increase in precipitation at a certain location projected by one model, and a decrease here at the same location for other simulations. While it seems to be somehow shifted, we have a decrease here, where in this realization there's an increase. So it's more heterogeneous. And the question is, if we want to assess the entire region as a whole, how can we do this to look at the precipitation extremes? So, and to do this, to start with this, we borrowed a definition of an index to assess the relative change of the area frequently affected by precipitation extremes in a region. So this was borrowed by Sonja Seneveratne, who applied this definition on a global scale to temperature. We tried to do it with temperature also on the regional scale, but it does not work because it's not. It only applies at heterogeneous patterns, so where it's patchy. On the regional scale, you either have a heat wave or not. So either all area is covered by the heat wave or not. So this does not work for temperature here, but it works for precipitation, as I will show you now. So we define here the DEX 20 as the area ratio of exceedance of the 95th percentile on more than 20 days per year. So we set several thresholds. We look at the 95th percentile here, and we define the reference, the P95 reference, as the mean of the 95th percentile over the reference period from 1971 to 2000 for each grid box. So we have, we look for each grid box, we calculate the 95th percentile separately because each grid box has its own threshold. Then we calculate an area in which the P95th percentile is exceeded on more than 20 days. So in this case here, in this small example, it's depicted in blue. So this is the blue dots are the area for a single year where the 95th reference percentile is exceeded. In this case, it's 4 dots. So in this case here, it would give 4. And the reference area is the mean of the areas in this 30 years. So for 1 year, I have the precipitation exceedance in these 4 points. We have the area of 4, let's say, for this year. In this case here, we have the same grid box where the percentile is exceeded, but this grid box is different, and here are some new, and the other one went away. But anyhow, there are 4 grid boxes, so we have again the area of 4. So there is, with this index, we don't see any change. So if you're exactly interested in certain grid boxes or certain areas, you cannot apply this index. It only works if you are interested in a certain region where you don't care where exactly this precipitation exceedance is happening. Then we go on to the year 2000, and as an example, there are 2 more grid boxes, so there are 6 here. So we have a ratio of 1.5 if we assume the area of the reference area of 4. If we take the mean out of this area, so we can see that there is an increase in an area that is affected by extreme precipitations. So what are the advantages and disadvantages here? We saw that the results depend quantitatively on the DEX threshold. So if I set the threshold differently, I get other values. But the relation between different simulations, qualitatively it stays the same. So it's useful for values that are heterogeneous in time and space, for example, heavy precipitation or temperature at the global scale. It's not applicable for values that are rather homogeneous, like temperature extremes on a regional scale. Okay, now let's look at some results here. What we plotted here is, again, for Scandinavia, the change in area affected by heavy precipitation. So this DEX 20 index I just defined is depicted on the left-hand side. On the right-hand side is the change in total precipitation as a reference for spring, summer, autumn, and winter. And we see here the 3 models, RCA4, Remo Realization 1, Remo Realization 2, depicted in different colors, and the solid line is RCP 2.6, the dashed line is RCP 4.5, and the dotted line is RCP 8.5 for the corresponding model. So this is just for a reference to depict it also here. What we see here that from the the DEX is smoothed here with a 30-year running mean, and the value is plotted on the last point of the period. This means that the value for 1980 is the mean from 1950 to 1980. So after the reference or after the historical time period, we see that here the area affected by heavy precipitation is increasing in all scenarios, more or less similarly. While it stops for the RCP 2.6, it levels out, and it increases for the other RCPs. So until the mid end of the century, there's a similar increase. But even for moderately increasing mean precipitation, if we look here on the right-hand side for RCP 2.6, for the 2 simulations from Remo, it's more or less staying the same, the mean precipitation. You don't see any increase here, but you see an increase in the exceedance in the area which is affected by this heavy precipitation. So there again, it's shown that for the mean precipitation here is not sufficient. Although we have for RCA4, we have in spring we have and also in winter we have a bump here, which shows more precipitation during this period, and this is a bit represented here also. So there's a quite correlation. To look at another area, the Mediterranean area, there's more variability here, But again, we see that there's a slight increase in the heavy precipitation events for RCP 2.6 compared to the RCP 8.5, which shows a strong decrease, which can be related here also to the strong decrease in summer, where heavy precipitation events happen in the total mean precipitation. While the increase in total precipitation here can also be associated here with the events, with the heavy precipitation events in summer. So in this region, we have a larger natural variability. Okay, coming to the summary and the conclusion. So there's an indication, because we only have 3 simulations, for an increase in area affected by heavy precipitation, RCP 2.6, until the mid of the century. And this index to apply to regional values, it's a compact index to assess the change in area affected by heavy precipitation. It can be relevant for adaptation assessments and could be also applied to quantities which are heterogeneous in time and space. And the idea is to apply this, if the simulations are there, to apply this to smaller scales and regions at higher resolution, because we go to more and more higher resolution, and then you are not interested if the precipitation is coming down at the left side of the street or at the right side, but maybe you are just interested in the whole town. And for this index could also be used. The plan is to do further studies to apply the DEX to other quantities and timescales, and to do a direct comparison with corresponding distributions. Okay, thank you for your attention.
Thank you. Thank you, Claas. We have time for 1, maybe 2 short questions. One thing that I was wondering was how much you showed early on some differences between different models in terms of the changes in precipitation. How much of that was tied to differences in how the circulation varies between those models? Have you had a chance to look into that?
Yeah, this was also an idea. We didn't look at it so far, but to associate the changes with the weather patterns, to do a correlation with this. This was also an idea which we want to do. Although the DEX value, it's on a yearly basis, so one has to look at distributions of weather patterns and to associate with this DEX value on a yearly basis. This is what one has to keep in mind. Okay. But of course, to explain this, then you have to look at the weather patterns. This is mainly for application, to give in a very concise way an indication of whether extremes are increasing or not in a certain region.
Good, thank you. Okay, it's time for coffee break. Please come back in 25 minutes at 10:50. I want to make sure we keep as close to schedule as possible. I'd like to thank all the speakers this morning for some very interesting presentations and also for staying on time. I'd much appreciated. Thank you.